We'll continue with our helicopter aerodynamics. We are still looking at vehicles in hover and possibly vertical climb. So we're looking at how to model the performance. Performance means how to predict the thrust, how to predict the power, these type of matters. Thus far, we have looked at two approaches. The first approach is called a simple actuator disk theory, actuator disk model, which is also called a momentum theory. It gave a lot of simple back of the envelope calculation methodologies. We were able to compute the hover ceiling of a vehicle, for example. We had a couple of worked out examples, and you also are working on homework number 1 using the very basic momentum theory or the actuator disk theory. We mentioned that the actuator disk model does not account for the number of blades, blade taper, twist, aerofoil sections, aerofoil tables, compressibility effects, Mach number, any of these things. Therefore, we developed later on a theory called a blade element theory, where we divided the blade into small segments, and then we looked at the angle of attack of each section, how much lift it is producing, how much drag it is producing. Then from that, we came up with the estimates of how much thrust that strip is producing and how much power that strip is consuming. Then we integrated it from root to tip to get the total thrust, total power per blade. Then we multiplied by the number of blades to get the total power and total thrust. Now we are going to come to a third and more sophisticated model where we are going to combine the blade element and momentum theory together. Momentum theory, which is the actuator disk model, and the blade element theory, which we looked at after that. So let's get started with the theory. So why do we need yet another theory? We noticed that that theory gave us a relationship for Cp, which is the power coefficient, equal to lambda times Ct, where lambda is the square root of Ct over 2 when the rotor is in hover, plus sigma CD naught over 8. The first term is the induced power. The second term is the profile power. We had to add a fudge factor called kappa, which is 1.15, to increase the induced power by 15%. It turns out this is because we were assuming the induced velocity to be uniform in our blade element theory. So this assumption underestimates the induced power by 9%. Okay, so that after 15%, it's showing up in this kappa factor. 9% is because we are assuming the inflow is uniform. Another 3% comes because it does not account for tip losses. What do we mean by tip losses? Because right at the blade tip, pressure is going to become equal. Upper surface and lower surface pressure will be equal, so that right at the tip you produce zero lift. But the 2D theory doesn't know anything about it. The slip theory doesn't know anything about it. It says the lift is still CL equal to lift curve slope times alpha. So we have to account for a tip loss factor. So we are going to put in a tip loss factor that comes up with another 3%. Finally, this theory does not account for the swirl losses, so that's another 3%. So this 15% correction comes from 9% from the induced velocity assumption as uniform inflow. So we are going to try to correct it first, because that's the biggest source of error is the induced velocity is uniform. So we are going to look for a theory which predicts the induced velocity in a somewhat better fashion. So that's what we're going to do in here. So blade element theory, as we mentioned, has got many assumptions, many approximations. And the biggest and worst assumption or approximation is that the inflow is uniform. So this leads to 9% out of the 15% correction. Kappa is 1.15. So out of that 15%, 0.15, 9% correction is because of this assumption. So we are going to look at how to correct it. Then we will also use a theory called variational calculus and show you that a uniform inflow is the best because it will produce the lowest power, induced power, therefore the lowest total power in many cases. So when you design a helicopter, you do try to make the inflow as uniform as possible, because instead of a kappa equal to 1.15, you want to make kappa smaller than that. It's like 1.06, 1.07. By making the inflow uniform, then you get a better design or a better rotor. So we will cover that a little bit later in this set of slides in this video recording. So first thing we do is we start with the actuator disk model, like that we did in the actuator disk theory, but rather than dealing with the entire rotor disk of area A, which is pi r squared, we assume that this rotor disk to be made of series of circular rings, concentric circular rings. A typical circular ring has got a radius of r and the width of delta r. Therefore, its area is 2 pi r times delta r. That's the area. Now, the velocity of crossing this ring is a climb velocity v plus the induced velocity of the rotor disk at this r location. So now we are allowing the lowercase v, which is the induced velocity, to vary from one concentric ring to the next concentric ring. So it's a function of r. So it's becoming non-uniform. So the mass flow rate is the area, which is 2 pi r, times density, times the velocity that is crossing the rotor disk, this ring, the velocity is v plus v. So the thrust is mass flow rate times change in the induced velocity. Far above the rotor disk, you don't have any induced velocity. You just have the climb velocity, capital V. Far below the rotor disk, you have a capital V plus 2v. So the jump in the induced velocity is 2 times lowercase v. So if you multiply the mass flow rate times the change in the velocity, you get the rate of change of momentum. So 2 pi r rho v plus v times dr, that's the mass flow rate, times 2 times lowercase v, then you get this 4 pi rho r v plus v times dr. So this is what we get from the momentum theory or the actuator disk theory when we apply it to not the entire rotor disk, but just a circular ring. Now we look at what does the blade element theory say about this particular radial location. We notice that the blade element theory says that each radial location you have a number of blades, perhaps 2 blade, 3 blade, 4 blade. So each blade has got a cross section like this. Okay, this is the aerofoil cross section. So the aerofoil sees 2 velocities. One is omega times lowercase r, that is the in-flame velocity. So the blade is rotating, so the aerofoil thinks the air is coming towards it at a velocity omega r in the direction parallel to the plane of rotation. The aerofoil also sees a vertical component of velocity, which is that climb velocity plus the induced velocity at the rotor disk, except now the little v is a function of radius. So we are going to allow it to vary radially. So the total velocity is the vector sum of v plus v, which is the vertical velocity, and omega r, which is the horizontal velocity. By the way, the angle phi is arc tan of, or tan inverse of, the opposite side, but the adjacent side. Okay. Now theta is the twist plus the pitch at that location is measured from the plane of rotation all the way up to the line of zero lift rather than all the way up to chord line. So alpha would be theta minus phi. Therefore, the lift coefficient at this particular section is a times theta minus phi, where theta minus phi is in radians and a is the lift curve slope. It's roughly 2 pi if you don't have any viscous losses. But if you have a boundary layer growing, we will correct it for a boundary layer correction. It will be roughly 5.7 instead of 6.28. Okay. 5.7 is the lift curve slope. It's a good number to use in many cases. Now, we know how much CL it is generating, so let's see how much lift it is going to generate, or the thrust. So I have B blades. So B, we have to multiply everything by the number of blades. Each blade has got a strip width of delta R. So the delta thrust is number of blade times 1/2 rho times velocity squared. Remember, the velocity squared is omega R squared plus V squared. The horizontal component squared plus the vertical component squared times the chord times CL times delta R. That's the delta thrust produced by this particular ring. Okay, all the airfoils, all the blades. Okay. Now CL we already had an expression for here, A times theta minus phi, where theta minus phi is theta minus capital V plus V over omega R, because phi is a small number in radians. The vertical component of velocity is in tens of feet per second. Capital V plus V is tens of feet per second. Omega R is hundreds of feet per second. Therefore, the ratio is a small number. So tan inverse of a small number is the number itself, as long as it's in radian. Therefore, the CL, we can write it as A times theta minus phi. So in the bottommost equation, we see theta minus phi is capital V plus lowercase v divided by omega R. That's the phi. That's the R tan of phi, but we write it as a phi itself. Now, omega R is much larger than capital V plus lowercase v. So when you square it, omega R squared is even bigger. Hundreds of feet, when you square it, it's much bigger than tens of feet when you square it. It's like a 10,000 versus 100. Okay. So we neglect the smaller quantity, capital V plus lowercase v squared, in comparison to omega times R squared. By the way, omega is an angular velocity in radians per second. Okay. It's not RPM, it's in radians per second. So we have two expressions for delta T. This is one from the blade element theory. This is the delta T from the momentum theory. So we combine the two. That's why this is called a combined blade element momentum theory. Basically, we equate this expression for delta T with this expression for delta T. So when you put side by side, you get a quadratic equation for the velocity squared. Notice that you have this expression that's got a lowercase v times lowercase v product term. So you get a quadratic equation. Before we solve for the quadratic equation in dimensional form, it's a common practice to divide all the velocities by the tip speed omega r. Therefore, the climb velocity v divided by omega r, where r is the tip radius, is called the climb ratio. Then capital V plus lowercase v by omega r is called the total inflow ratio. And lowercase v by omega r is sometimes called the lambda I, which is the induced inflow ratio. Anyways, if you non-dimensionalize everything, then you still get a quadratic equation, and you have two roots. So we pick the root that is appropriate, which is positive. So the lambda positive root, because the induced velocity should be positive going down to the rotor disk. So we pick it, we get this expression. So this is the total induced inflow velocity from the combined blade element momentum theory. Notice that now it's no longer a constant, it's a function of radius. Because the solidity, which is B times C over pi times R, B times C divided by pi times capital R, may be varying with radius. Theta, which is the twist plus pitch, may be varying with radius. There's an R over capital R, which is definitely varying with radius. Therefore, lambda is now a non-uniform induced velocity. We do notice that a lambda can be made uniform if theta is inversely proportional to 1 over lowercase r. And if you make sigma a constant. That means if you have a rectangular blade and theta is varying as a 1 over lowercase r, then you get a uniform inflow, which we, as we alluded to, will produce the lowest induced power. Such a thing is called an ideal induced power. Therefore, when theta equal to some constant over lowercase r, that's called an ideal twist. Okay, so the inflow is no longer uniform, it's varying with radius. So if theta is a constant times capital R over lowercase r, then for constant sigma, then you'll get a constant lambda everywhere. Then you'll have a uniform inflow, which produces, as we will show, the lowest induced power. Therefore, this particular type of a twist distribution is called an ideal twist distribution. This is not recommended because near the root it produces huge amount of twist. Therefore, the root section may stall, because it's at such a high angle of attack. And also dynamic stall will occur much more because it's operating at such a high angle of attack. So vibrations will be very high, especially in forward flight. Therefore, ideal twist is very seldom used in practice. It's just a nice conceptual information. That's nice to know type of an information. So why do we say inflow should be uniform? So let's look at the power induced. Power induced is, for each ring it produces a delta T. In hover, climb velocity capital V is 0. Therefore, you only have the induced velocity crossing the rotor disk. So velocity times force is the power, induced power. So V times dt is the induced power. We had an expression for dt up here. So if capital V is 0 in hover, then dt is 4 pi times rho r times lowercase v squared times v dr. So when you multiply v times dt, you get 4 rho pi r v cubed dr. Okay, that's the induced power. How about the thrust? We just sum up dt. So it produces 4 times rho pi r v squared dr. So it's got a 1 less v. You don't have the induced velocity multiplying it. So we want a thrust. We want it, that's good. So for a specified thrust, we want to minimize the induced power. So we want to know what type of induced velocity v. We will minimize the induced power p induced for a specified t. Therefore, what we do is calculus of variations as a good way of minimizing functionals. So whenever you have a constraint, such as a thrust, specified thrust as a constraint, what you do is you take the function that you want to minimize, then minus some Lagrangian multiplier, in this case we call it beta, times the constraint, which is thrust. We minimize the combination. So we say p minus beta t should be 0. That means the variation of p minus beta t, which is delta of p minus beta t, should be 0. That means delta of p, which is defined on the top of the slide, minus beta times t is defined in the top of the slide. Both have an integral with respect to r, so you could group them together as a single function. Now, delta is like a derivative, it's like a derivative, but it's operating on the integral. So since the boundaries of the integral are constant 0 to capital R, you can take the delta of the integrand. Okay, so v cubed will become 3v squared times delta v. V squared will produce 2v times delta v. Okay, so when you do that, you'll get an expression that is shown in here. So this should become 0. There are many things that are varying. Rho is not a 0, pi is not 0, r is not 0. So how can we make this 0? It will become 0 if the term in the square bracket 3v squared minus 2 times beta v times v, lowercase v, is 0. Since beta is a constant, a Lagrangian multiplier, it follows that the v must be a constant. Okay? Because beta is 3 over 2 times v. So if beta is constant, induced velocity is constant. Therefore, variation calculus says uniform inflow produces the least induced power for a specified level of thrust. Therefore, if you want to make the inflow uniform, you have to ideally twist the rotor, for example. Then the theta times r over r will become a constant. Then you have for a constant sigma, constant solidity, you get a lambda equal to constant. But as I mentioned earlier, ideal rotor only optimizes the induced power. It produces very high angles of attack because theta varies like 1 over lowercase r. So the closer you are to the root, higher and higher twist, higher angle of attack because alpha is theta minus phi. Higher the alpha, the more the chance of separated flow, drag, higher profile power, higher stall, and so forth. Okay. Therefore, also such ideally twisted rotor is hard to manufacture. It performs very poorly in high-speed forward flight because of the dynamic stall. So helicopter designers strive for what they call optimum rotors, which minimize the combined total power, which means it minimizes the induced power plus profile power. So they not only change the twist, but they also change the chord by changing the taper. Okay, the chord is varying as a function of r. So this is the process that is done for an optimum rotor. So first thing we do is in an earlier slide, don't pay attention to slide number 72 because it used to be a one giant presentation. I have broken it into smaller segments, slides for recording purposes. But you may remember we saw that for a figure of merit is minimized if the average CL over 3/2 over CD is maximized, okay, or CD over CL power 3/2 is minimized. Okay. So what you should do is you should pick an alpha. Remember, as you change the alpha, CL changes, CD changes. So alpha versus CL versus CD is a table. So compute CL raised to the power 3/2 divided by CD as a function of alpha, and pick an alpha that will maximize CL raised to the power 3D over CD. So the CL that you are going to use, this is called the optimum CL. Okay. Now once you have the optimum CL, since alpha is theta minus phi, you can solve for theta. How about the induced velocity? Because now it is uniform inflow, we can go back to our actuator disk model, which is V over omega capital R is square root of CT over 2. So this is how you will twist the blade. Okay, so you select an alpha that maximizes CL raised to the power 3/2 over CD, then use it in this expression to solve for theta. So this is the blade twist distribution. How about the chord? How do we change the chord for an optimum rotor? Remember, our dt from the blade element theory is the first equation in this slide. dt from the momentum theory equation is the second equation from the slide. You equate the two. We already know CL, so we can solve for C. Okay, so it's very easy. BC over pi capital R, which is the local solidity. If you do some algebra, just group it. Rho cancels out everywhere. dr cancels out in the two expressions. CL will be there. Omega will be there. Everything else will be there. B will be there. C will be there. So BC over pi R works out to be the expression shown here. So this is how you will taper the blade. So the blade will be highly non-uniform, non-linear taper. So if you plot it, it would look something like this. Such a blade is hard to manufacture. So very often the people will go with rectangular blades, or sometimes they will taper right near the tip region. Because tip produces a lot of thrust, tip also consumes a lot of power. So if you look at some of the Blackhawk rotors, UH60A had a rectangular planform and rectangular swept tip. UH60L or M, I've forgotten, one of them had a tapered rotor right near the tip. So our theory says taper is good. You want to reduce the chord as you go outboard. That's what this equation says. Chord should decrease as R increases, lowercase r increases. So by tapering the blade, you can improve the performance of the rotor. So we have accounted for the 9% of the kappa. Kappa is 1.15. 9% correction is the inflow, non-uniform inflow correction. So we have covered it. So now we look at the tip loss. Remember, right at the blade tip, our actuator disk model and our blade element model says it's still producing a CL of A times alpha. But we know right near the tip, the pressure will be equal because the bottom side, top side, the pressure will equalize. So the lift coefficient should go to 0. So we want to correct the tip region. So we use a model that is developed by Prandtl. Okay. We will not derive it. We will just take it from his model. He developed it for fixed wing and also for propellers. We are going to use it for helicopter rotors here. Okay. Basically, he said first define a function called capital F, which is defined as 2 over pi times r cosine of e power minus of lowercase f, where lowercase f is b over 2 times 1 minus, where you are radially r divided by the tip radius divided by the lambda, where lambda is the inflow velocity, induced inflow. Induced inflow non-dimensionalized by the tip speed, therefore it's a inflow ratio, induced inflow ratio. Now we notice that when B is infinity, that means the infinite number of blades, F will be infinity, e power minus infinity will be 0, arc cosine of 0 will be pi over 2, then capital F will become 1. Okay? But for finite blades, for when B is finite, the only time when F will become very, very small and go to 0 is right at the blade tip. When a blade tip, small lowercase r equal to capital R, therefore 1 minus r over capital R will be 0, lowercase f would be 0, e power 0 would be 1, r cosine of 1 is 0, therefore capital F is 0. How about near the root and elsewhere? F will be increasing, so it will steadily increase from 0 close to 1 in the inboard region. Then it will become, so F will change smoothly. It's a smooth function. So Prandtl developed this model for fixed wings, tip losses, and it's also been used for propellers by Glover. So this is what we would use in our case. So how do we build it into our combined blade element momentum theory? Very easy. We know that the tip rings is not going to produce any lift. So we multiply the dt of lift produced by each ring by multiplying by F. F will smoothly go from 1 to 0 at the tip. Therefore, the thrust produced at the tip region will be 0 automatically. So if you build that in there, then you'll get a combined expression for the inflow. So that's the combined inflow model that we will use. Okay. So I think I'm missing one slide here that I'm going to show you in my next iteration. So let me see where that slide is located. It's in part 1, version 2. My apologies for missing that slide. Okay, so this is the resulting inflow velocity. So you build that F in, so you get an expression for lambda that involves the Prandtl function. We notice that the lambda is a function of capital F. But we previously saw f is a function of lambda. F is a function of lambda. So it's a catch-22 situation. So what we will do is, you will assume initially f equal to 1. Then you will solve for the lambda. So assume f equal to 1, solve for the lambda. Then put that particular lambda here to find the little lowercase f. Recompute capital F, iterate until it converges. So this is how we would do it. So there's a slide missing that I'm going to put that down in here. So it'll be all the slides would be there in your PowerPoint stack when you review this particular video. So thanks. We'll put a stop at this point.